First, thanks Pierre for your introduction. And in my group, we are working on the machine learning, and we combine machine learning with experiments. For example, we use active learning and also reinforcement learning to discover new materials. Second direction is we work with combination machine learning with computation method. For example, we combine machine learning with DFT calculation, and we can find the machine learning operation. Then we can use that to do monitor isolation, phase field, and even analytic calculation. The third direction is we combine machine learning with the incentive monitor, so we can do the policy management. And currently we are working on the auto lab for material, not for chemistry. So today my topic is about the self-supervised probabilistic model for material design with enhanced structure information. Okay, so in this talk, we first go the background of data-driven material design, and then we talk about the architecture of our machine learning model, and then we'll show two cases. One is the design new sheet metal alloy, and also we do the bandgap engineering for highly abstract. Firstly, in recent years, the data-driven approach has been widely used in material design. However, the present data-driven approach mainly focuses on the matching from composition to property, and they neglect the crucial rules of critical structure. Actually, our purpose, we have to build the relationship between the composition, structure, and the property. For many advanced materials with function analytic, we've already showed the strong correlation with the crystal structure. For example, for sheet memory alloy, it is based on the reverse multi-symmetry transition. It transforms from high symmetry parent phase to low symmetry monoxide. And the crystal relationship between monoxide and parent phase is a group-subgroup relation. On the other hand, for the highlight perovskite, its performance is really on the AB X-ray structure. Distortion by strain or doping will break the symmetry and change them under the band gauge, then change the optical and electrical properties. So actually, the relationship between composition, structure, and property is very important. To improve the machine learning accuracy, it's crucial to embed the structure information to the machine learning model. Actually, there are several ways. One way is you can directly use the descriptor, which can describe the structure information. The other way is you can use the the structure info, like graphic structure algorithm. One of these algorithms is a graph neural network. This one already showed great promising, just because this method naturally encodes the atomic connectivity and structure information. Compared to the composition only descriptor, this method can show more accuracy. But this method requires a large amount of labeled data with known crystal structures. However, the labeled crystal structure data is always very difficult to get. For example, the experimental characterization of the crystal structure with the desired property are labor intensive. Computation method, for example, DFT, is also costly in both time and the policy and the money. For example, for the calculation of the sheet memory effect, you have to the DFT calculation requires frequently adjustments to the crystal structure get by the phonon dispersion data. Of course, you can use the combination of DFT and heuristic algorithms, for example, OSPAC and Calypso. This kind of method can reduce the time, but still time consuming. This limited lead to the scarcity of the labeled crystal structure data. Actually, the scarcity of labeled crystal structure is a common bottleneck in material demand. For all the open data site, seldom have both the information of the crystal structure and the properties. For example, for sheet memory alloy, we know a lot of data sites they have the crystal structure, but we don't know whether they belong to the sheet memory alloy. So this limits the model's ability to establish the composition, structure, and property relationship. So how to solve these problems? We found, on the other hand, that the public data site, they have lots of unlabeled crystal. For example, the material project, they have a lot of data sites, but they also carry the valuable information about the composition and structure relationship. And how can we leverage this kind of information to improve the downstream property predictions? Actually, one solution we found is a self-supervised learning method. This method can mask and predict the element in the unlabeled crystal structure. Then they can learn the automatic representations that encode both composition and the structure. Thus, this one can boost the performance even with limited data. Oh, sorry, I don't know what happened. This is a schematic flow of our method. We call this self-supervised probabilistic model. The first step of this model is the training process. We use the labeled crystal structure to train the GNN model. And then in the inference step, we just create different crystal structure and with the mask atoms and then fit the GNN model. After that, we can, this kind of trained GNN model can build the atomic representations, and we can also calculate the probabilistic model. And then we can build the model composition and the structure criteria based on these two steps. And finally, we can use this criteria to build to discover new materials. Actually, what I want to see here is that we didn't do any DFT calculation anymore. We just learn the atomic representation from the unlabeled data site, and we calculate the probabilistic model. We calculate the conditional probability, and then we can predict the most possible materials that fit your property. About this model, we have two very important steps. The first step is representation learning. Actually, in this step, for given crystal structure, all the items of a specific element are masked. Actually, this mask means they act as the pseudo label of the masked crystals. And by mask and training the GNN models, then you can predict the atomic representations. And this is the how to say the GNN structures, and in the fully connected layers, they can decode all the atomic representations. So, for example, in every atoms we have the atomic representation, including the information of elements and also the crystal structure. And we also make some comparison to make sure our atomic representation is okay. So we calculate the Spearman correlation between our method with the existing physical properties. And we found that our method shows strong correlation with the atomic radiance and the number and also the electron mag activities and also this kind of behaviors. That means our method shows strong relationship with the physical properties. And we also do the benchmark against other descriptors across the crystal property data set. These are well-known data sets, and these are well-known descriptors. And we found that among all these kind of well-known data sets, our method outperform than the other type of descriptors. This is just because our method is embedding the structured information. And the second step of our method is the probabilistic model. And actually, from our GNN model, we can calculate the conditional probability of this and this. With these two probability, conditional probability, we can calculate this conditional probability, this one, and all this one, all the other three. In this case, we have to mention that A and B means the element, element and the concentration. And Y means the crystal structure. X means the lattice constant. So for all of these four factors, if you know both of them, this method can calculate the other one, the other two. So you can do the inverse design and structure prediction. For example, this one just means once you know the crystal structure and the lattice parameter, then you can predict the elements A and B and its combination. And also, this one means once you know the crystal structure, you can predict combination element A and B. And this one means once you know the combination of element A and B and the crystal structure, you can predict the lattice parameters. So this is for the B2 structure. If we know the B2 structure and the lattice constant from our method, we can predict top 10 elements, top 10 alloys which fit this properties. We can know this nickel is well known, is an alloy, but not all of them is the Xi'an alloy. And also, if you only use the B2 lattice, we can also use our method to predict top 10 alloys. And also, once you know the crystal structure, you know the elements, you can also predict the lattice constant. This is for B2 structure. And also, we do the B3 structure. And for the same case, you can predict anyway, for the three cases, you can also predict them. And also we do it for the L1-2 structure. Once you know the lattice constant, the crystal structure, you can predict the alloy. And also, once you only know the crystal structure, you can also predict the AB. And also the once you know elements crystal structure, you can also predict the lattice constant. But here we show that once you know the elements crystal structure and once you predict the lattice constant, the constant lattice constant error is very small. And that's the above three is only for the binary alloys. We can also do it for ternary alloys. And for example, once you know the elements and the crystal structure and the lattice constant, so we can predict binary alloys. This one, nickel, ammonium, and gallium, this is well known binary alloys, and also the others which are not well known. And for the circuits, okay. Then we can use our model to do the predictions. And actually, these are top 30 alloys predicted by our method. And the green one is real. After we check with our knowledge, we found the green one. Only 1/3 is real Xi'an alloy. The 2/3 is not Xi'an alloy. That means the accuracy is only 1/3. The reason is that the data set for the well-known chip memory alloy is only 0.2%. So you only use the data-driven method, the accuracy, not so accuracy. Then we have to add the structure information. For example, for shape memory alloy, we know the parameters is usually we have the B2 structure, DO3 structure, or a 1,2 structure. So if you add this information, that means the structure information to this model by the probabilistic model, then we can calculate, we can predict. This is still the top 30 by the composition method. And this once you add the probabilistic model, and then we can find the accuracy increase to 64%. And once we increase the likelihood threshold to this value, also we can increase the likelihood threshold to this value, and then the accuracy will increase and furthermore. Okay, so by combining these two ways, self-supervised learning method and also the probability model, we predict 15 alloys, and we found under the 23rd is already no alloys, but we still have the 27, which is unknown compounds, and never discovered. So that is just do the data-driven and combine with the crystal information, so you can predict some new materials without any DFT calculation. Okay, so then for among the 27 alloys, we just do DFT calculation for one alloys, and this is we call this magnesium gold alloy. This alloy we calculate the parameter, lattice parameter and crystal structures, and even the photon dispersion spectrum. And we found that the parameters at the mountain side is they change from the B2 to platinum. This is obviously group subgroup relationship, and also, and from the photon spectrum. From the photon spectrum, we found the mountain side didn't have any imaginary mode. That means the mountain side is stable. And also, we also calculated the volume change, and this volume change is -1 is very small. So this kind of transition is very the volume change is also very small. And we also calculate lambda 2. That means the interface distortion. And the lambda 2 is very close to 1. I mean, it's a lambda 2 equal to 1. That means the lattice interface distortion is 0. So this is for this alloy, we found the four properties. We have the group subgroup relationship, magnesium phase with stable, and low volume change and small interface distortion. So this is just prediction. We got an experiment. We are not doing an experiment, but because the gold is very expensive. Okay. So the second case, the previous talk is mainly about the intermetallic alloys. But for example, we have for the solid solution crystals, we have some problems. For example, for the highlight perovskite, both the A side, B side, and X side can be doped, and the dope will change the formation energy and the Fermi level. So in this case, we develop our method to a nested graphic regression model. In this model, we have two graphic graphs. So one is structure graph, which include the structure information. The other is composition graph. For the structure graph, the edge is a bounding relationship. The node is the composition graph. For the composition graph, the edge is the element interaction, and the node is the chemical elements. So we just develop our previous model to this kind of nested graphic regression, and then we can use this model to represent the composition and structure. We also do the benchmark for the solid solution and data set. These are well-known data set, and we compare to the most well-known ROST method. And our method will show the improvements for all the data set. That means our nested graphic model outperforms the ROST method, especially for the solid solution alloys. And we also did comparison for the banded graph and for formation energy for the training data set and the test data set. And based on this kind of training model, we predict the doping effect. Once you add the, I don't know, CL, BR, and R into this kind of alloys, and the energy change. And we also do the DFT calculation. We show that once you add BR into these crystals, you will find the banded energy decrease. This is consistent with our calculation, with our prediction. So based on this model, we can do some prediction. For example, if you want the banded graph with change from 1.3 to 1.4 EV, and this is the solar photon energy and range, and also we want the, for example, the formation energy is less than minus 6.5 EV. Then we use our model, we can predict the new material. This material is these materials, and we do the DFT calculation, and we found the banded graph is 1.39 bucks. Very close to the prediction to our requirement. Okay. So in conclusion, here we introduce two methods. One is we can use this self-supervised representation. This one is this one can effectively capture the atomic representation with the structure information. And then we also add the obviously this method with the probabilistic model, and this one can effectively search the stable structure. The combination of these two methods can give us a method to predict the new material with the desired structure, stable structure, and then from the properties. And for this kind of solid solution alloys or structure, we will find the nested graphic model. This model can work in both ordered and disordered crystals. That's all. Thank you very much.
Any questions?
Thank you very much for a very nice presentation. And you very briefly showed the perovskites. And on the perovskites, you mentioned about band gap and band gap prediction. So
Yeah.
how good is the model reliable on the band gap prediction on perovskite, especially you mentioned against the DFT simulations?
Currently, we have do this kinds of prediction only. How good is we just do a few experiments. We just do the prediction with our model and then do the DFT, but it only shows the tendency very good. For example, this is pure one. This is one. When once you add the BR, you decrease to 1.224.
And then you're matching mainly halide perovskites. How about ceramics?
Ceramics.
Yeah.
It's also okay.
It's also okay.
It's even easier.
Yeah, even easier.
Yeah, because here is because you have the solid solution, the
Right.
solid solution atoms occupy the lattice site randomly. So you have to deal with it random occupation behavior. So that's why we use the nested method. Nested graphic model. One is for structure, one is for this kind of random occupation behavior.
And if you would allow me one more question, it's stretching a little bit further than it, but Your model is mainly about structural predictions, with electronic properties prediction.
Yeah.
Halide perovskites suffer from degradation. Do you think that a degradation function can be added to the
Okay, actually here for example, we have the pseudo label.
Okay.
The pseudo label means, for example, if you want to study machine learning part, you have to learn, pre-train with the algorithms in memory part. So this is pseudo label. So once you have this pseudo label, then you start found the most stable structure. This is something like the DFT calculation.
Yeah.
But we didn't do any DFT calculation. So this prediction is very fast.
Thank you very much.
Okay.
Yeah, my question is related to the graph models.
Oh.
They tend to be very complex. To do machine learning predictions and computations, descriptors are very complex. What did you use to make faster computations or predictions?
Yes, actually, previously people use at very beginning, people will predict the property only use the decomposition. And then people also add some structure descriptor and combine the combination descriptor to predict properties. But actually they never the structure descriptor doesn't work very well. So once you use a this kind of a graphic algorithm, I don't know, it's very complex. But once you build this kind of graphic algorithm, it's very efficient.
Yeah, and look at the details or the picture for the self-supervised training. So understand that you must, you said you must the atoms, but what is when you then predict with the the objective function, for example?
Okay.
Yeah.
Okay, go on. Here. For example, just give you one example. For example, 10 nickel. If you mask nickel as a mask atoms, but in our world, there are lots of alloys which contain nickel elements. So we learn the structure and also the environment of nickel in all the alloys. Then we can get an atomic representation for nickel. That means for all the alloys, nickel have only one atomic representation. Okay, this is what we learn. This is a graphic never learn. Once you know this one, and then you will know. Once you know this kind of atomic policy representation for all the elements, actually it already includes the crystal structure. Okay.
Thank you.
Just in addition to that question, what do you mean by environment of nickel?
Environment.
Of the nickel, so to learn.
Okay. For example, in B2 structure, it's a BCC B2 structure. You have nickel. Okay, nickel is either in the bottom, in the bottom or let's see.
The chart.
Yeah. Okay. It's just B2 structure, but the nickel can also for example, you can also use some BO3 structure, and also I12 structure, and even the hexagonal structure. But what we here we are keen on the nickel and its local chemical environment for all the structure. Then you get one descriptor for this nickel for nickel. Okay.
It was maybe about further question. But the problem behind schedule, but just a quick question here. That prediction is PD functional, I guess, right? So it goes up to 6 CV if I read correctly. So what matters is the bandgap accuracy. If we need to go right, we correspond to about 0 to 2 from the DJ function, right? if you look at the R2 and the measures like RMSE, just in the visible range, what are they? In some previous works, if you look at, 5, 6, 10 EV, then everything is really and beautiful up to, you focus on the visible range.
Okay.
There's no predictors.
Okay, what I want to say here is that I'm not expert on the parasite. So this is just, some people ask me to get this property, so we do prediction. So we can discuss later, once you have the more realistic requirements, then you can do prediction. Okay.
Very well. Let's take the speaker again. Thank you very much.